Okay, so we have our first invited talk is coming up for this session is coming up. Giuliano Taffoni from INAF is going to be talking about all the shades of the cloud.
Good morning, I'm Giuliano Taffoni. I'm working at the National Institute for Astrophysics in Italy. It is an honor for me to open this session on cloud computing at different scales at this Virtual ADAS 2020. Thanks a lot for inviting me at this conference. When ADAS invited me to make this talk, I tried to figure out how to shape it and also how to interpret this concept of different scales. And as my research activities focus on cloud and high-performance computing, in particular exascale technologies, I decided to outline the discussion to give a different perspective. So something that gives the idea of the importance and the ongoing efforts for the convergence of those two technologies. And on the other side, to discuss also the different scales in terms of computing size and collaboration and progress sizes. This talk is organized in two parts. First, I will examine what research has been particularly successful in the cloud, and then what we can expect from future evolution of cloud computing, in particular on the area of high-end data analysis and high-performance data analytics. That I think is a particular interest for our communities, especially with the advent of new instruments like SKA, CTA, LSST, but also LOFR2, for example. In particular, because in the near future, what will become really important is to compare big data coming from theoretical simulations and observations. Let me open a parenthesis. During this talk, I will make some example. I know there is a lot of ongoing activity, and I will not be able to cite everybody and everything. So, I mean, there is much more than I will be able to discuss here. Also at this ADAS, there are posters, both interesting presentations. Another point is that I will mainly focus on public clouds, and I will only cite briefly the role of private and open science clouds. I'm not actually really a fan of public clouds, but I think they are offering interesting features, and I think that it should be interesting to discuss about the use of them. Being the first speaker of this session, I want to open my talk dedicating 2 minutes to a very short introduction on cloud technology, and then I will discuss how it relates to high-performance computing. So, cloud computing is the on-demand delivery of resources via internet with the pay-as-you-go model, and this fascinating but unreal theoretical idea of infinite resource capability. So, the more I need, the more I can request, and if I have enough money on my credit cards, the more I can get. Cloud was based on virtualization and later on containerization. Containerization is a really interesting technology because it allows to encapsulate software that can be deployed rapidly on cloud, but also on high-performance computing resources. And I think that this technology will play a central role in the way we are using cloud, but also in the way we are using and we will use and we will work on high-performance computing cloud convergence. Cloud services operated by Amazon, Google, Microsoft are commonly referred as public clouds. This distinction between private and public clouds, but also community cloud, open science cloud, may appear minor, but it has important implication because the majority of the clouds operate at scale far larger than any private cloud. So they can offer different services and glue together different services from the infrastructure up to single software. I'm not saying that public cloud are better. I'm just saying that we can use them profitably if we, for example, implement an hybrid approach to build open science cloud or project clouds that are also able to use the capability of public clouds. While I was analyzing this talk, I tried to understand what is the status of the computing power offered by high-performance computing and cloud. And while the top 500 project gave me the estimate of the actual size of high-performance computing resources, I was not able to find similar information for public cloud infrastructure. Well, you can find investment, but not exactly the amount of resources in the different cloud data centers. I was surprised at that, and if you have, for example, this information, please let me know. I will be really happy to add this on the paper or and improve this presentation. But I think there is a reason for that, and this is intrinsic on the different nature of high-performance computing and cloud computing. High-performance computing and cloud evolved independently, driven by distinct optimization criteria and to answer to different requirements. In particular, the cloud, roughly speaking, of course, evolved to process the torrent of business and industrial process. So also what to expect and how the two entities, how the two technologies evolve is quite different. For example, the HPC community emphasized efficiency in terms of application execution efficiency or energy efficiency. Myself, when I'm using a high-performance computing resource, I'm trying to optimize my application as much as possible on the specific hardware. On the other side, cloud and big data communities tend to emphasize the user experience and scalability. The hardware is similar, but the programming models and tools and the underlying software markedly differs. I mean, on one side, in the case of cloud, you have high-end data analysis and analytics tools based on Hadoop or statistical tools like R or machine learning tools. On the other side, what you have is more the standard shared memory approach based on MPI libraries, on high-performance libraries, and optimization and debugging tools. The HPC focus on to offer a unique platform with shared memory approach. Cloud resources are designed for an increasing proliferation of hardware, being it processors, memory size, disk size, capabilities, accelerators, FPGAs, to target different applications. For example, now there is an emergence of numerous hardwares to support machine learning, like maximization FPGAs, and this is offered by cloud computing. Anyway, both high-performance computing and clouds are based on data centers. Data centers in cloud terminology are the so-called regions. There is an interesting paper that summarized the work of big data and exascale computing project in US, written by different authors including Jack Dongarra, that highlights the fact that in recent years there was a split between high-performance computing and high-end data analysis, and consequently from a split between high-performance computing and cloud. In synthesis, they discuss and conclude that very roughly the high-performance computing world today is focused more on numerical experiments, clouds more on data analysis and analytics, and this reflects, as I was mentioning before, also on the way cloud and HPC evolves and are implemented. However, this is slowly changing, driven by the needs to explore the rising flow of data from new instruments and sensor systems, not only from science, probably less from science and more from the Internet of Things, smart cities, industrial and business data. But anyway, I will discuss this later in the second part of this presentation. But now let's see how cloud computing is used by astronomy and scientists today. Well, it is true that the interest in infrastructure and in tools for doing large-scale data analysis in the cloud was and is driven by private companies to process the data, in particular data related to social network or business. Consider that according to Cisco, by 2021, around 1,000 exabytes of data would be stored in cloud data center, and about half of them would be processed. And in general, cloud data center will process the 94% of workloads on internet. So I mean, huge numbers. However, also scientists are approaching the use of cloud computing, in particular for the use of computing resources. And a lot of experiments have been done recently. For example, as LSST tested the use of cloud Kubernetes capabilities from Google. But there are a number of cloud infrastructures, some of them are listed in this slide, and are both a science platform developed for use of the cloud or cloud itself, dedicated to astronomy. There are many papers that are showing our experiments on the cloud. What connects almost all those experiments is a quite similar use of the serving model and approach. In fact, we can use cloud in very different ways. An elastic computer or a cluster to use them when you need computing resources, as a service again, or as a container platform. You can use it as a programming platform or as a laboratory assistant, a source of software that can perform certain tasks in software as a service manner. Even if there is a lot of space in astronomy for software as a service, I think that because, just think in terms of software that we can offer in the same way we're using, I don't know, Google Docs or tools like that to find and manipulate images on your own data or on data offered by the virtual observers. This is a software that we could offer as a software as a service. I don't know, I'm thinking about Aladdin, but there are many others. But the main effort in astronomy communities are now on infrastructure as a service cloud or container as a service cloud for computing. And this is also common to many other research communities. In practice, cloud is offering computing infrastructure for small and medium scale collaboration with the large scale computing demands that happen sporadically. That's the way we are using the cloud today. What is important is that the research group wants to experiment faster, and this is happening because you may have a very dynamic use of the resources with the right size that can grow or reduce according to the needs. And those computing resources can be expensive or cheap according how you use them. There are complete cloud economy models to estimate the cost. But at coarse grain, we can say that upload data is for free, computing can be cheap, download is very expensive. So the reason why computing is cheap is because of spot instances that are widely used in science. These spot instances represent cloud access capacity which a cloud provider needs to have available for any customer demand. Public cloud offers this excess capacity at a massive discount to drive usage. However, they can shut down these resources when they want. So and terminate the spot instance with just short term. So if your application is aware of that, so for example is able to automatically resubmit to a new spot instance the particular computation is doing, well, this is a good way of using the cloud and also cheap one. There are many examples of the use of the cloud by astronomers, and I will cite some of the activity that has been done by INAF. INAF recently acquired some credits from Amazon, and it is offering those credits to its researchers on the basis of proposals that identify the best software that can profit of the use of the cloud. Here I have 3 different use cases that I'm mentioning that are interest for different reasons. One of them I think is particularly, I would cite this because it is the use of window cluster. That is not something very common to have in our computing center. And this is a good example of a use of public clouds that are offering, of course, again, if you don't need continuously, but they are offering some resources, also with an interesting pricing model, because with window cluster you have to think also in terms of window licenses, and the licenses is itself inside the offered by the cloud provider. Another representative example of the use of cloud computing in science is this observation simulation for Cherenkov-Sterkov's array work done by Landoni et al. They develop a framework to deploy and execute different realization of the application on different AWS spot resources in parallel. They use in practice an HPC approach, and they containerize their software to be executed on a Kubernetes cluster. This framework benefits of different AWS functions and capabilities as the Lambda function as a service functionalities. In practice, they compare the result with the one obtained on a local resource for a Crab Nebula observation simulation, both in terms of time to solution and price. And what is working here is the fact that they are using more resources at the same time than the one that they have on their computing center for a smaller amount of time. So in practice, the computation is faster and the splice is lower. And this works for a sporadic use of the resources. So if you use them sporadically for a small amount of time. And the other good thing of using public cloud for this kind of work is that you can use the own grant for doing that, even if the price, I think it was around 1,000, 2,000 euros for all these experiments. This same approach, I think it does not fit too much on the other side for big projects. If I was a big project, I would prefer to have my own private cloud, so a project cloud for my own users, and eventually extending these to public clouds using a hybrid cloud approach. Well, this is the way we are using the cloud right now, but the cloud is evolving, and as I was mentioning before, there is space for the user, a lot of use of software as a service, but also there are other service models that the private cloud are offering, like analytics as a service, so machine learning tools on cloud, on your own data, or on distributed data, or on public data, sorry. But there is another service model that I want to introduce that is related to the high performance computing and this convergence with the cloud. The necessity of convergence of high performance computing and cloud has been recognized by different authors already and different authorities. In 2015, for example, the Executive Office of the US President emphasized the importance of big data and high performance computing ecosystem convergence. And this has been echoed in Europe. The Commission communication on the European data infrastructure and the European Open Science Cloud emphasized the fact that high-performance computing has been completely absorbed into the broader digital single market, and it only has to appear as a component of this global system. Similar considerations have been done in China and in Japan. The reason why we are thinking in terms of a singular or a convergence, let's say, between high-performance computing and cloud and big data and high-performance computing is driven by the fact that the size and complexity of data produced by the new instruments, I mean, sky is the future, but LOFAR 2 is arriving, LSST is here, and the user and the multi-message astronomy requires a significant data reduction with computing resources and method typical of the high-performance computing. Distributed memory system, hard optimization on the hardware, HPC system software, and so on. And this will happen both for data analysis and data analytics. This is already now happening in other disciplines. For example, the high-throughput X-ray tomography generate high-throughput mosaic tomography corresponding to 160 terabyte per images, so per images, and they need to correlate more of those images at the same time. So this requires high-performance computing approaches and methodologies. The same thing will happen in astronomy too. We need high-performance computing facilities become a sort of nodes of a more complex network of resources able to support workflow consisting of multiple and divergent applications. For example, high-performance computing, machine learning, visualization, all the same in the same infrastructure. So this allows to combine in the same environment both simulations and data reduction. So I mean, here I'm just saying that in practice what happens is that you need to move your computation to the data, and the data is both theoretical and observational one. Public cloud already recognized the need to offer high-performance computing resources, and in fact Microsoft Azure and AWS and the Amazon AWS are offering high-performance computing as an infrastructure as a service. I've tested Azure last month, and I think it's really close to what I can expect from a high-performance computing system offered by Praise, for example. However, they are infrastructure as a service. So in practice, even if there are scripts, even if it is web-based, even if you have APIs, anyway, it requires some system management capability. So you need to know what you are doing, because at the end, what you have is a sort of, you are building a cluster USSH on top of it, compile your application and let it run. So what we want is something more than infrastructure as a service. What we would like to have is a sort of high-performance computing as a service. So execute the code without the complexity of setting up an HPC infrastructure on the cloud, and this requires to couple our code with the resources. And this happens if, for example, we are using, and we can do that, and this will happen if we are using, for example, containerization technologies on one side. Then if we are able to describe both our software and the computing resource with metadata, with a set of metadata, and if we are able to couple this with the data, with the observational data, so with the data lake. In the framework of the European-funded project ESCAPE, we are developing a tool that is a proof of concept of high-performance computer as a service. Yesterday, Stefano Russo presented this tool in the science platform section, giving a different point of view, a microservices approach to create a web-based platform to support interactive computing. However, I would like to give you a different perspective to the same work. The tool has been designed to execute containerized workloads in Docker or Singularity on a number of different computing elements that are offered by the platform to its user. And it can be autonomously selected on the basis of the user need. So they can be high-performance computing cluster or high-throughput cluster or even public clouds. On the other side, it has been designed to allow users to set up and run their own containers, so their own software, again, autonomously. Being a component of the ESCAPE Science platform that is developing, and so it will offer a data lake, in the future this tool will also couple with the data, so in practice we will be able to couple software, computing, and data. And as ESCAPE is also developing a software marketplace to access a large amount of scientific tools, if necessary, we can be able to access this marketplace too from the platform, from the science platform. Yesterday, Stefano described this tool in detail. So I'm not going to enter the details also today. Here I would like to emphasize its capability to couple our own software with computing resources into a task and to mask the complexity of the use of the resources. Software containerization allows to create closed environments that can be used not only to deploy software but also to improve experiment reproducibility and software preservation. On the other side, each resource offered by the platform may be different. So it can have different CPUs, different memory, different partitions. They may have accelerator of different kind, but also software of different kind, high-performance computing software of different kind. And if we manage to describe each resource through a metadata, we will be able to identify the best platform for our code. So, in the last days, in the last years actually, we are discussing about the importance of software annotation, well, containerized software annotation, using metadata for different reasons. Well, here I'm adding another one in practice. So, together with the platform metadata description, it will be extremely useful also for the use of high-performance computing as a service cloud. Otherwise, it could be quite difficult to couple software and computing and eventually also data. Right now, our work is just a proof of concept, and it is obviously missing a number of features to become a real high-performance computer as a service system. But it is facing a couple of interesting hot topics. One of them is of course the problem of bringing code to data, and the other one is this idea of high-performance computing on cloud. There are, of course, other efforts on this direction. We are not the only one that are thinking in these terms, and there are major activities from Atos Bull that is developing a portal to hide the complexity of the use of high-performance computing cluster. And also Forte in Greece is working on a containerized-based infrastructure for HPC. So I mean, there is a lot of efforts, and I will not surprise if in a few months or years we will have many other tools to access computing resources from HPC computing resources from the cloud. This tool now is used on our HPC cluster to make interactive data reduction for the local Italian community, or as shown here, to make spectral analysis using AstroCook. So it's not something that has been just developed. It is used already, even if outside the framework of the ESCAPE Science platform. Okay, so let's go to the conclusion and some further thoughts. In this presentation, I tried to couple two different topics, the scale at which we are now using cloud computing resources and some of the results that we have, and future trends, in particular on the era HPC and big data. Even if cloud is offering simplified access to different kind of resources, it is not so easy to deploy cloud infrastructure or services. It requires some expertise that not only all the scientists have, in particular for more complex setup like an HPC cluster. So a cloud, both private or public, should allow to build and deploy science platform on top of it. So the science platform is the way the science interact with the resources and the data. And on the other side, cloud should simplify the design and deployment of data lakes. Public clouds are already offering some data lakes capabilities based on object storage or other kind of distributed file system like HDFS. However, I have the impression that the kind of data lake that we have in mind is something a bit more complex, something that somehow is able to collect data coming from the edges, from the instruments, and on the other side also, for example, to manage the transition between cold and hot data, so some more, let's say, some features that is more related to the scientific activity. The new trends are driven by the necessity to process complex large data sets using new approaches to data analysis, including machine learning and deep learning. This means that cloud infrastructure should be able to provide not only machine learning analysis tools like the analytics as a service deployment, but also computing resources able to process data in an HPC way. This is also particularly interesting for us because we would like to use the same platform and data lake for theory and observation. Well, I have the impression that we are focusing a lot on cloud as infrastructure as a service or as a container as a service. On the other side, the software as a service model is something that we should investigate much more, in my opinion. A number of tools that we are using on our everyday life fits on this approach, and we in principle we can use them on top of our own data, but also on IVOA distributed data or data lake storage data on the cloud. So I have in mind things like, I don't know, Topcat or Aladdin that we can try to offer from the same infrastructure in a software as a service way. Well, again, as I was mentioning before, I'm not really a fan of public cloud. I think that we should have our own resources because these help us not only to satisfy the requirements of our user, but also to improve our technological knowledge. However, we should not demonize public cloud. In fact, any researchers like campus, institution resources, national computing center resources, private institutional cloud resources, well, also public cloud can become an addition to this portfolio, and because they are useful in particular if you are able to identify what are the best use cases for the usage and which kind of computing or services we can deploy on them. This is the approach that we are pursuing in ENAF, where we have supercomputing center agreement with CINECA, we have institutional resources, HPC, HTC, and cloud, and we also have an agreement with Amazon for public cloud access. We are offering these full portfolio resources to our researchers that can request them on a proposed-based evaluation, and we are quite happy, I have to say, with this approach because we are able to distribute the different loads on different kind of resources that we have. I'm not sure, for example, that public cloud approach fits on large projects. They should rely on project infrastructure. Maybe it could be interesting on the other side if a large project, when they build their own internal cloud or infrastructure, will be able to implement the possibility to access also external resources, in particular public cloud resources, using a hybrid approach. But I have the impression that this may have some advantages on one side because, of course, we are avoiding vendor lock-in because we are using our own resources. But on the other side, we can also access external services and tools that are changing a lot with time. I mean, there are always new offerings inside the public cloud infrastructures. And you never know in the future if you need more resources or some specific tool that is deployed on the public cloud. So here is the end of my talk, and these are the people. Thank you for listening, and these are the people that work with me and help me in preparing this presentation. Thanks a lot.
Hey, thank you for the talk. We have some time for questions. So if you can either put it in the Q&A and in Zoom, or else if you want to put something in the talks channel in Discord, we can pick it up from there. So actually, I'll start off with a question of my own. You had touched upon using hybrid approaches, but you had also mentioned that one of the more expensive things you can do is downloading data. You know, uploading was free, but downloading could be costly. So how do you handle, how do you kind of bring those two together so you're you know, you have some stuff on-prem, some stuff in the cloud, but you're not incurring high costs?
Well, the idea is that if you want to reduce the cost as much as possible, the idea is to use the public cloud resources in an hybrid approach as much as possible for computation. So uploading the data, it's something that is for free. So I mean, and many times when you are processing data, you have the possibility to download only the final analysis that you have done on all the data. So I mean, I have the impression that building an archive, for example, of astronomical images on the cloud could be quite expensive. But on the other side, if you just use the computing resources and you are processing images and then, for example, extracting just the observable and download them, well, it is quite cheap. So you can do that. It is not a place where you have to store, and unless you are using tools like Glacier that are long-term storage for data that no one is using, so backups or very cold data. It is not a place where you would store data that you are accessing too much. If you're using them inside the same data center, so without downloading it, it costs I mean, just cost the storage. But yes, that's the only way of doing that.
Okay, and we have a question from Discord from William. He's curious as to why you are not a fan of public clouds.
Well, no, I'm not a fan of private clouds. This means that in practice, I think that it is anyway important to have your own private cloud and to grow in the experience and to improve your experience on the cloud on something that you can manage yourself. This means that then I also appreciate all the functionalities and all the capability of public clouds that for sure can offer, also because they are improving very fast with time, can offer new technologies to test that can be useful for your research activity. But in practice, I have the impression that anyway you have to develop your own computing background and technology background with your local installation. So I mean, I don't think it's it's wise to rely only on public cloud.
Okay, do we have any more questions from anyone? I don't see anything in the Zoom Q&A. I don't see any more questions in Discord. So I guess we'll thank you once more.